So I will say welcome back everyone to PCB Design Fundamentals Part 2. You heard us chit-chatting there real quick about auto backup in Altium to not lose data if you're working on a project. In the meantime, before we get started, finishing up the slides and then working on the project this week, does anybody else out there have any questions either on material we covered on Monday, project work, material we've done so far in previous, or just general questions, Altium or other, any other questions out there before we get started?
I had just a general question, kind of related to the backup.
Hmm.
Um, I've been recently going and trying to use the project releaser function,
Okay.
Altium 365.
Yep.
Uh, just curious what your views on that is.
I will be 100% honest. I have never used the releaser. When I left industry, they had not yet fully fleshed out and released Altium 365. They've only released that since I've been teaching. I've been teaching, doing this professional teaching going on 5 years now, like late 2017. Actually, no, longer than that. We'll call 2018, so 6 years now. So the releaser was something they started when they first proposed it. It was for internal company databases, right? A way to connect to your Windchill or TeamCenter or whatever your database system is, because they hadn't yet developed the fully fleshed out the 365. So the companies I worked at the time had their own release process using that. So I will be 100% honest, I have honestly never used it. From what I've read about it and like user comments in the user forums, everybody does seem to really like it and say it works very well. I have zero firsthand personal experience because I do 100% teaching now, so I don't actually do new designs at a company where I have to release the design that way anymore to like a
Gotcha.
separate server, right? All the designs I do in consulting and things like that are just like, well, here's the file. I make you, I
Right.
use the project packager to make that self-contained zip if the company's not on 365,
uh
but don't use the releaser,
Right.
if that makes sense.
It's kind of funny you mentioned Windchill. Some years ago, we went with Windchill, and they could not, for whatever reason, get Altium integrated into the system.
Yeah, wind chill has been notoriously difficult. Part of that, I think, is the fact that Windchill is now was owned by PTC, and PTC, along with Valor and Mentor Graphics, has all been acquired by Siemens. So and since Siemens owns Mentor, I think the majority of their focus on system integration of Windchill has been on their own product family, the Mentor Graphics products and their product family. They're working on it. I know Altium claims they now have hooks into it, but from my understanding, is they're much more efficient with hooks into TeamCenter than Windchill.
Yeah, essentially what they wanted us to do was just package it up and then put it into Windchill.
Yeah, that's what I ended up doing. The companies I was at that used Windchill, that was exactly what we did. We literally created the zip file, the packager, and just push that zip into Windchill rather than trying to do the full hook and loop releaser that the releaser style. So
Right. Okay. Thank you.
yeah,
Appreciate
not a
that.
problem. All right, great question. All right, are there any other questions? Once, good
I
question.
have
Yes,
one
Kevin.
question. Were we supposed to receive like a password or anything for signing into the IPC account for Altium?
Uh, as I recall, Kevin, you're a late addition to the class. Yes.
Yes.
Okay. So for that, what I'm going to have you do, the rest of the class has already gone through this, and I've actually been going over this multiple times now. I will put 2 email addresses down here in the chat window. So my email, and then we've got a general education 2 email account. If you want the license for Altium from IPC, send us an email, to those two email address and tell us what email address you would like us to use. And the reason we say that is we have found over time, our experience has been, if you are registered with IPC for the class using like your corporate or company email address, right? We have
Yeah.
found over time that companies like Altium and Mentor and Cadence and those kind of things know who the IT people are at all these companies, especially if you've ever even had like a demo license before. And we found that even though we try to sign you up directly, that the email gets sent to like an IT person, which it shouldn't be. So we usually recommend providing us a personal email, Gmail, Yahoo, whatever, um, kind of email address, and then we'll register the license, and you'll receive an email directly from Altium with your credentials. Says, yep, that email address you gave us is assigned. Here's your password credentials. First thing you have to do is log into the um, Altium Live, basically the user area, and from within there you go download. I actually have a video on that. So if you go up here to our IPC Edge page for the course, under the how-to videos right here, I have
Yeah.
Altium download, install, and setup that walks you. It says, here's the email you should have received. So myself or others at IPC can set you up with the license. We just need to know which email address you want us to use.
Okay.
Be cognizant. If you've ever tried Altium before, say got a trial license or anything like that, um, using a certain email address like a personal one, we won't be able to use that one for our license. It has to be a clean email that is never signed it and registered with Altium before.
Uh, is
Um,
it is if we already have an Altium account through, like, say, our company, is it necessary to have the Altium account with
no, and
IPC?
that I was just getting to that. If you already have an existing Altium account that you are using, that you are free to use for this class, then the only thing we need to know is, again, reply the same to and say, I already have an Altium account. This is the email address I sign into Altium with. When you start Altium and it says you sign in up at the upper right-hand corner, signed in. So just tell us which email address you're using to sign into Altium, and we will add you to our Altium 365 cloud storage area because we are taking advantage of Altium 365 for assignments, and as well as I'm really in love with the commenting capability in the 365 for classes like this. It makes my feedback process uh, far easier, far more efficient. So,
Okay.
um, so yes, if you already have one and you're able to use it, like we have another student in another one of my classes who says, well, technically we have licenses for the company, but we have such a small pool and so many other people using it that I can't use it for the class. So he still had to sign up with his own personal one. So as long as you've got access to a license that you're able to use for the class, like say through your company, just then let us know here. I already have an existing Altium license. Here's the email address I used to sign in, and I can quickly add that to our 365 account. All right. Okay. Any other questions before we get started? And Kevin, I'm going to assume you did get the email from Ivan with your ability to log into our Edge page here. Yes.
Yes. Yeah. And I sent the email with my work email to try to get that to, but
Okay,
you
you just sent
just
that
stated
over.
that I
Okay.
sent it, like, maybe, I think it might have been Monday or this weekend. I sent it. I was just seeing, I didn't get a reply yet. So, but you said
Okay,
it was
I
Monday.
may have missed it. Do me a
Okay.
favor then, while we're sitting here in class, to just me then, the Christopher Moyer one down here. Just send that again, and I'll look at it when we go on break today.
Okay. Thank you.
Yeah. All right. Great. With that, let us go ahead and get started. We do have a number of slides to finish up from where we left off on Monday. We actually had a lot of great questions on Monday, a lot of great comments. So we didn't get through all the slides on Monday. So let me quickly go through the rest of these. These will hopefully go a bit quicker, more pictures, less words kind of slides. So as we know, all traces on a printed wiring board will behave as a transmission line, or hopefully know, and we will learn more about this later when we get to signal integrity discussion, which I believe is either next week or week 5. Um, but anyways, we will get to we will see and learn, if we're not already familiar with this, but hopefully we are, all traces on our printed wiring boards are transmission lines. For the digital traces on our design, we need to design those or define those, characterize those as controlled impedance traces. There are 4 physical parameters that are used to define the impedance of a transmission line. Specifically, a transmission line made up of the traces on our board, right? Um, Slightly different equations if it's a circular conductor and a high power transmission line up on the power pole, etc., um, and so on. So those 4 physical parameters for the circuit board, printed wiring board, transmission line are the width of the trace, the thickness of the trace, the height of the trace above the return or mirror plane, and the dielectric constant of the laminate material. Now, one thing I'm going to point out early here, it'll come up in more detail when we talk about controlled impedance design in signal integrity, but from the point of view of materials, right? Talking earlier on Monday, we were talking about the isola materials and the different dielectric thicknesses and the fact I can have different dielectric constants for the same thickness. And I was pointing out, the 3.8 versus 4.2 dielectric constant here. Here I went all the way down to a 3.6, and that is actually possible to happen in our board materials here. But just to look at, so I'm going to use the characteristic impedance here of a dual strip line. We'll see this equation here in just a moment. But assuming an internal layer dual strip line structure here, using the first order algebraic approximation equation here, and assuming that I have a 5 mil trace width, 6 mil height to the plane, 1 mil trace thickness, meaning so 1 ounce after processing, and then 2 dielectric constants here. One material has a dielectric constant of 3.6, the other has a dielectric constant of 4.2, right? So not even a whole integer number difference between them, about half an integer number, a little bit more, 0.6. So basically half of an integer number difference between the 2 dielectric constants. If my target impedance, characteristic impedance that I'm trying to target, is 50 ohms plus or minus 10%. So with these parameters here, at 5 mils, 6 mil height, etc., the material with 3.6 mil dielectric constant gives me a calculated nominal characteristic impedance of 50.5. So I'm almost dead on to my target, and so I have plenty of margin. If nothing else changes, I leave the 5 mil trace, the 6 mil height, the 1 mil thickness, etc., and the only thing I do is allow the fabricator to choose a different material that's at 4.2, all of a sudden my characteristic impedance drops all the way to 46.8. Now, most people would say, well, you're still within tolerance. The problem is this becomes the nominal characteristic impedance. And then remember that there's the fabrication allowances, right? The fabricator might over etch or under etch, overpress, underpress, and so on. We'll talk about all that next week when we get to manufacturing. But we don't want the design itself to already be this close to being out of spec, because that means any slight variation in the manufacturing of the board because of the fabrication differences or tolerances in fabrication means that I can very quickly and easily have an out of spec condition on that characteristic impedance. So we can see just how much my characteristic impedance changed just by allowing the different material dielectrics, even within that same resin system like we saw on Monday. Yes, a question. Looks like Mattia.
Hi. So, let's say tolerance should we be targeting in
What's that?
general, or what kind of let's say tolerance for the characteristic impedance should we be targeting? So is it something let's say
So there's
is it
not a
system?
tolerance. So there's not a tolerance on dielectric constant. That is a physical property of the material. The tolerance that you're allowed is to specify what is your allowed tolerance on characteristic impedance. Now, by default, most fabricators out there, if you don't explicitly state it, are going to give you a plus or minus 10% on whatever characteristic impedance you give. That's their go, no go. Many fabricators out there now can achieve plus or minus 5%, but you're going to have a little bit more engineering hand holding, a little bit more engineering controls on the processing, maybe a little bit higher incurred cost. But yes, when we talk dielectric constants right here, this is a fixed number. This is what you have to design in, and this is where you have to run the tools like we see in Altium, or third-party tools like Hyperlinks or Polar or SI Wave and so on, to calculate and say, I can allow, if I go 3.6, I might be able to go 3.55 to 3.65 to keep my characteristic impedance right here. I will say, my personal experience, whatever characteristic impedance you're targeting here, 50 ohms, 75 ohms, or so on, you should try to maintain about plus or minus 1 ohm right here. So I've allowed 49 to 51 ohms as my acceptable range of target impedance before manufacturing. Just because, I might not be able to get to exactly 50, I might have to go to 4.752 mils, which is unreasonable for a fabricator. So I go to the next higher mill and so on, or dielectric thickness here, right? Height to the plane. I might have fabricators say, yeah, I can't do, 3 decimal places of dielectric thickness. I can do whole integers of dielectric thickness, or whatever the case is, or 1 decimal place, and so on. So based off of what your fabricator says, I typically target about plus or minus 1 ohm from my true desired as my acceptable, right? If I'm building my stack up and I go in and I look and I see that the characteristic impedance that it calculated is like I had here, 50.5, I'm like, yeah, close enough, that'll work. But if it had come in something like this, I'm like, nope, I've got to change that. Okay. Does that answer your question, Mattia?
Yes, thank you.
All right, excellent, great. Any other questions before I move on?
I have a question.
Yes.
Have you, in my experience, like when you get down to like say 40 ohms for like say DDR or something like that, and you put down plus or minus 10%, in my experience, I've had the fabricator come back and say, oh, can you do like 15%, or like we'd like to do 15 plus or minus 15%. I know the traces are a lot thicker and stuff, but like I don't know what draws them to do that. Like I figure if they
Okay, so here's the problem. It's not so much what the impedance itself is. It's the trace width, right? So the fabric, and we're going to talk about this next week, and hopefully you guys will put this together. The narrower you make your trace width, say, I want to get sub 5 ohms right here, right? I've got a 5 mil, I'm sorry, not 5 ohm, 5 mil, right? I've got a 5 mil trace width, right? So typically the fabricators have a plus or minus 20% on the width of the trace itself. Now, plus or minus 20%, right, on a 100 mil wide trace, for example, seems like a large number, but the reality is that the actual chemical etching processes used to fabricate the traces, it doesn't scale linearly like that. It's typically about plus or minus 1 mil, right? So let's assume that my etching capability, that going through the etching, can modify my trace width plus or minus 1 mil. Well, on 100 ohms, plus or minus, or 100 mil wide trace, plus or minus 1 mil, that's 1%. I'm still nearly target width. But if I try to do plus or minus 1 mil on a 5 mil or 4 or 3 mil wide trace, because I'm doing thinner and thinner to get the more and more traces in the area, well, now plus or minus 1 mil on a 3 mil trace is a huge percentage of trace width, which means rather than changing dielectric constant, you're changing this W value here by a much more significant percentage, right? And so they're basically saying, we're going to these narrower and narrower traces. We just can't hold the tolerance on that because of our etching process and the variance in etching, where if you could run your DDR, but run your DDR using 5 or even 10 mil wide traces, yeah, they could still easily hold the plus or minus 50 ohm or 40 ohm at the 10% tolerance. And my suspicion is that the DDR is pushing you to use the BGAs or even the micro BGAs where you're sub 1 millimeter pitch for the memory chips themselves. Am I correct in my assumption?
So for the breakout, I kind of was loose with about that, but for the main track, it was, smaller than 5 mils for sure.
And that's where you're running into the problem. As you get smaller and smaller and smaller in trace width, the fabrication tolerance on the ability to etch that trace to exactly that width is becoming a greater percentage of that width, which is causing that greater variance in Z0.
So is it safe that to achieve like the 10% tolerances, it's like 5 mils is kind of like the
I've done plus or minus 10% on 5 mil for 30 years with never a problem at a fabricator.
okay,
Below 5 mils is where they started balking a little bit.
gotcha.
Yes, Mattia, another question out there.
Sorry, a follow-up question now. Is it in the case that we can actually play also with the thickness of the dielectric to get, let's say, that if we cannot go so low with the width of the trace to get the impedance, then we can play with the electric thickness, right? Or
Yes,
how much of the
basically
core or
there's
prepreg we have.
four, right, exactly. There's 4 physical parameters. There's 4 dial knobs you can turn. Width, thickness of trace, thickness of dielectric, and dielectric constant. That's the 4 physical parameters. Now, thickness of trace you usually can't play with because that's dictated by the copper of the layer, right? If you do 1 ounce copper, you've got a fixed thickness. Width, dielectric thickness are basically the 2 knobs you can turn because dielectric constant is going to be set by the material. Like we saw, I'm going to pick the one with the appropriate amount. So yes, you can absolutely play with dielectric thickness and trace width, but there's a caveat to dielectric thickness, and we will see this when we get to signal integrity. The thicker you make the spacing between the trace and the return plane, the larger the field loop areas for the E field in the EM wave, which means the larger the H field or magnetic field, which means the greater amount of crosstalk and inductive cross coupling between the aggressor nets and the victim nets for crosstalk analysis. And so, yes, you could go thicker to try and play with those numbers, but so you might get the controlled impedance. However, if you make your dielectric thickness too thick, now your loop areas are so large that you get so much inductive coupling that now instead of being able to route a bus at like 5 or 6 or 7 mils gap between the copper features, I need 15 or 20 mils gap between the copper traces. Otherwise, I get excessive crosstalk. And we'll see that when we get to signal integrity.
Great. Thanks.
Yep. But absolutely great questions, everybody. Okay, moving on. So, speaking of those parameters we hear. So while we have these first order approximations given in the IPC 2221 standard, these equations here, I'm going to say 2 statements here. Number 1, a 2D modeler or 2D field solver minimum should always be used. Altium has one built in. Siemens, who owns Mentor Graphics, had also bought this tool Hyperlinks. Hyperlinks is an exceptional 2D field solver for doing the controlled impedance. Polar Instruments, which is one of the manufacturers of the actual TDR test equipment, makes a tool as well. And there's some 3D field solvers like HFSS or SI Wave from ANSYS and other tools that do full 3D Maxwellian equation field solving for full EM field. You should always rely on 2D field solvers. These algebraic equations, these are first order approximations, and several of them have caveat conditions and or they break down under certain conditions where the 2D field solvers do not. Additionally, your fab house should always be consulted. As we were just talking about, there's tolerances on the process or process controls that the fabricator has. When they say they're going to etch, how close, how much over etching do they typically get? When they laminate, the pressure, what hydraulic pressure are they using? What temperature are they using, etc. And all of these factors are going to control the subtle variance in dielectric thickness, trace width, and so on. So while you're designing around a nominal condition, you should always consult your fab house. They have years, if not decades, of statistical process data, databases that they use that they know how to dial in the stack ups based off of their internal processes and what kind of adjustments they need to make. Okay, so my thing when I'm doing controlled impedance stack ups professionally, First step I do, I build my stack up, and before I ever lay my first trace on the board, I send the stack up to the fabricator I'm going to use and say, verify my stack up meets meets all of your process, and tell me what adjustments you'd like to see. And if they come back with any adjustments, I feed those into the tool, and therefore I know when I'm designing, there won't be any surprise gotchas when it goes through the fabrication process. But then looking over here at the first order approximations. The first transmission line structure we're going to have is our two outer layers. We call these surface microstrips right here. This is where I have dielectric constant below, a reference plane, the width of the trace, the thickness of the trace. And we're given by this equation right here. So we have height to the plane, width, thickness of the trace, and dielectric constant. Now, there are, with this one, there's two caveats to the characteristic impedance equation. Again, since these are first order approximations, this is only valid between about widths of about 5 and 15 mils. Again, as Kevin was mentioning, he's had run into issues with fabricators, traces being too narrow, the math stops working, traces being too wide, the math stops working. You get too much variance, right? Additionally, this particular form of the equation is only valid for W over H less than 1, right? So basically, the height between the trace and the plane must be greater than the width of the plane, right? W divided by H must be less than 1. If W over H is equal to 1 or greater than 1, again, this form of the equation starts breaking down. Not with 2D field solvers, but with this first order mathematical approximation. Looking at that again over here, there's also, we could do the characteristic capacitance of the trace over here. Got some notes. We don't need to go through any of these. This is just propagation time in nanoseconds. We will see another form of the propagation delay calculated relating rise time with rise time, dielectric constant with speed of light. That's where the 11.8 actually comes from here, is a speed of light issue. So we'll see a more easier calculation of that over here. Okay. Then we have the next form of the equation. This is what we call a strip line. This is where we're now on an internal layer where I have a single signal conductor, all right, signal trace between a pair of planes and fully surrounded by dielectric constant right here. So now I have an H above and H below, a thickness, and then I have the two reference planes and a width right here. So I have a slightly different equation here for characteristic impedance and characteristic capacitance. This is the one, by the way, that we just used in that example I showed you. Then we have a third form right here, the dual strip line. This is actually going to be our most common structure that we're going to use in most of our modern board designs, because this allows me to have two signal layers adjacent to each other, assuming that one signal layer is primarily the horizontal traces and the other is primarily the vertical traces. And I will be able to, therefore, I won't have significant capacitive coupling between the two signal layers, and therefore I get the benefit without having to have too many extra reference planes in my design. I'll be able to have the benefit like this right here. And again, even more complex form of the equation. Tools such as the Saturn PCB toolkit, that's another tool out there. I have a link to that on our Edge page. As we've seen, that's a free tool from Saturn PCB Design. And again, they give away their tool for free. It's a nice tool, but it does have some drawbacks and caveats right here. One of the things they used to state in their software version 7, they since have taken the statement out, but I have not seen any statements from them saying they're now using a full solver here. But what they used to state right here is their calculator for characteristic impedance is their own formulas under the hood. They're not directly implementing the IPC formulas, but they do not have a true 3D field solver engine. Instead, what they've done, they make this assertion here: the calculator uses a complex formula, not the simplified formulas. The results, they claim to track the Sonnet 3D field solver, but I have seen no white papers or third-party data analysis from them that proves that it does properly track a 3D, and I have no direct first-hand experience with Sonnet. under how that tool works and how accurate that one is, that I do have with the ANSYS tools, the hyperlinks tools, and so on. So basically, they claim they've come up with their own complex mathematical formulae that closely track a 3D field solver, but I have no firsthand knowledge of that. And since it is a freeware tool, I always take everything with a grain of salt. And again, back to my original statement, your fabricator is your friend. Contact and work with your fabricator early and often and have them help verify, because they will have statistical process data that says, we've actually fabricated a board, we measured the impedance on it, we know what these materials and our processes, what you can expect out of the characteristic impedance, and so on. Okay, last couple of materials we're going to talk about here. Solder mask. Solder mask is used to protect the exposed copper, the exposed bare copper traces on the external layers from oxidation and other environmental contaminants. Basically meaning after we fabricate the board and we have the external layer, the purpose of solder mask, it actually does two things for us. Any bare copper that's not going to have soldering to it, like the surface mount pads or through-hole pads, needs to be protected from oxidation, right? Historically, in older boards, we would do the protection from oxidation by going in and coating the entire board in solder. You would literally take the bare board, dip it in molten solder, pull it out, blow the excess off, and that's how we would protect copper from oxidation and contamination. The second and probably the more primary use of solder mask, it's called solder mask for a reason. It also prevents solder bridging during the reflow process. Historically, traces, I said, were protected using a solder finish on the entire board. However, that was back in the day when rise times were so slow that signal integrity was not a problem. And the non-uniformity of the thickness of the trace after you coat it in liquid solder mask and blow the excess off, you basically get this non-uniform thickness. You get this wavy thickness to the surface of the solder pads there. And it led to much signal integrity problems, and the signal integrity started becoming an issue. The overall thickness of the solder mask is going to be determined by the trace thickness of our board. The solder masks we're going to use are what we call liquid photoimidrol. They will be applied in a liquid form and then hardened or cured using either heat energy or UV light. Both styles exist. UV thermal actually being more common. And so it'll be applied as a liquid, and so due to the flow of liquid solder masks, some areas, primarily corners of traces, will have thinner solder masks than valleys or peaks of the traces. This leads, again, to a slight non-uniformity in dielectric performance of the trace and the mask. You may need to specify multiple coats of mask to achieve proper corner thickness if you are trying to rely on your solder mask in a dielectric performance capability. While solder masks do have a dielectric constant, and a voltage withstand, they're typically not designed or typically not used to actually act as an insulator. They're really there to act as an environmental protectant and to prevent the solder bridging during the soldering processes. If you do too much solder mask, you can have a solder mask that is too thick on the surfaces, excuse me, for some SMT compounds, which can lead to a phenomenon called tombstoning. Okay, so what do I mean by solder mask thickness? Well, since we're applying this as a liquid, when we apply liquid over the surface here, the liquid that's up here on the top of our component, our trace right here, I should say, due to surface tension of a liquid, that liquid will tend to flow off of the surface and start to fill in the valley here. At some point, however, the force of the fluid being pulled off will be exactly equaled by the force of the fluid that's already down here pushing back, and we'll get this dome of solder mask here, this trough of solder mask here, and what we end up with is we have a maxima point right here at the center here, the peak of the dome, and we have this local minima at the corner, which you can kind of see right here. Here's a cross section where I've got inner layers of the structure of the board right here are the materials we talked about on Monday, but you can also see up here, here's a trace on the surface, and here's the solder mask material. You can see how much thicker the solder mask is right here, adjacent to the trace, than it is right here at the corner. You can see how the solder mask got extremely thin right there at the corner. So if you are attempting to have a minimum solder mask thickness at the corner right here, it may require the fabricator to put 2 or more coats on. Do 1 coat, let it cure, and then come back and do a 2nd coat so you can build up this thickness. But again, if you do that, you're also going to get more thickness here as well as here, and the solder mask in between here may extend high enough that if I'm trying to expose some surface mount solder pads, the part is no longer sitting directly on the pads, but sitting on this pedestal of solder mask. And then during the soldering process, the force of the liquid, the paste when it turns liquid, can pull one end of your chip resistor over, and the whole thing flips up on end vertically in what we call tombstoning. Historically, solder mask was applied manually by someone with a squeegee and a screen. This could lead to misregistration of the solder mask on the pads. I'm assuming we've all seen this at one point. You get your board in from the fabricator and you look at it and you notice that the solder mask is kind of offset from the solder pad itself. Again, there are allowances in IPC, especially in the 6012, the fabrication standard, that tells the fabricator how much they're allowed to misregister and still consider it a good board. If you require 100% of your pad open, you need to document that on your paperwork, as well as have that available. What do you call it? Have that available to the fabricator. Okay. Now, newer machines are automated instead of an employee with a squeegee and a screen printer. They now have, it's still a screen here, but now you've got a more mechanically aligned structure right here. You can do some optical alignment rather than just a guy trying to line up with a screen manually. And the application is a more uniform squeegee process and so on. It's going a little bit more uniform. And we'll look here. We'll look here shortly. We might wait till next week, but Tayo America is a manufacturer, one of the leading manufacturers here in the States. And actually, Tayo is a Japanese company, so I believe they also cover Asia and Europe as well. They just have a different branch division that covers Europe and different branch that covers Asia as well. But Tayo is one of the leading manufacturers right here. Because these are chemical properties in a liquid state, right? Similar to other chemicals that we would use, anything that is chemical-based processing, the fabricator actually has to deal with this quite a lot because of all of their intermediary processes, solvents and etching chemicals and acids and all that. Anytime, though, that you are dealing with a chemical-based, chemical nature of the raw material, there is both a technical data sheet as well as a safety data sheet. In the old days, it was referred to as an MSDS, and a material safety data sheet. Now it's just an SDS, safety data sheet. These are, and I will ask the question, is anybody out there not familiar with the old MSDS or the newer SDS? It's the same thing, just a new name. Anybody out there not familiar with what these are? Oh, good. Everybody knows safety data sheets. Basically, safety data sheets, they contain all things like reactivity, chemical exposure, oxygen exposure, PPE requirement, basically all the stuff that EMS and firefighters and first responders and poison control needs to know if you accidentally get exposed to this stuff, right? If there's any badness that can happen, and so on. I will also make comment, IPC standard, IPC-SM-840, SM for solder mask, defines the requirements of the solder mask. Now, I can't stress this enough. We will talk about this more next week in manufacturing. Just like the 4101 that we looked at on Monday, described the individual, materials. If you'll notice, absolutely nothing in 4101, however, told a fabricator how to process those materials. They were simply, here's the requirements of the material, right? What was the T sub G? What was the decay? What was the peel strength? And so on. It effectively looked like a data sheet like we would have for a resistor. The same thing is true here. This SM840 standard here is a material standard. It describes the electrical, chemical, mechanical, etc. Properties of the material. Nothing in this document here, however, tells a fabricator how to actually apply this material to your board. Nothing about flow rate or temperature to process at or any of that nature. That comes from our 6012 fabrication standard as well as directly from these manufacturers for how to apply their materials. So far we've talked solder mask. We'll look at one of these data sheets here in a little bit, time permitting. Yes, was there a question out there? I saw a mic starting to open up.
Yeah, I would have waited a little bit more, but I just wanted to ask for the top solder, actually, for the top solder expansion that you have actually set on all the pads. Is that something which is done to combat, let's say, possible misalignments,
Yes.
or is there? Okay.
Yes, it actually is. The solder mask expansion is done specifically to mitigate the misregistration. Now,
Okay.
now I will qualify that as saying in IPC 7351, which we are currently using in the class as the footprint standard, we actually had a value in there. I believe it was like 3 mils. But there's a couple of things, and we can talk about that after break when we get to the remainder of the. I'll start working it out, Tim. The newer standard, 7352, actually defines that in the library, you should set your expansion to 0. If you do need to make expansions, do them at the design level. We'll explain what we mean by that later. But the problem is, as parts have gotten smaller and smaller and smaller, and processes better and better and better at the fabricators, rather than us trying to design that solder mask expansion at the board level, we should leave that up to our fabricators now based off of their processes. Or at a minimum, work with your fabricator. Because the old rules of thumb are breaking down as our parts are getting so ridiculously small. Additionally, there's going to be a minimum, what we call a sliver width for the solder mask, as well as the silkscreen, which we're going to talk about next here, which is there is a minimum line width that the fabricator can actually print a strip of the solder mask in. So if it gets too small, there's some things we can do about that. So remind me, if not today, remind me next week during manufacturing, and we'll talk about that some more. Okay? So we talked solder mask. Next, we're going to talk silkscreen right here. The technical term we should actually be using is legend. Silkscreen is actually a process for applying it. The technical term is legend ink, and we'll talk about that here in a minute. But in the same way that Tyo America makes the solder masks, they also make the inks that we can print on the boards for our text and our references and so on. Same statement due to the chemical nature. And where IPC SM840 defines the properties of the solder mask materials, IPC 4781 defines the requirements of the silkscreen or legend ink materials. Historically, legend was applied manually by a worker with a squeegee, just like the solder masks. This led to harder to read text and limited text sizes, because anytime that I have a material of any thickness and I put a liquid in there, the thickness of the screen, no matter how thin it is, that is a vertical wall that's preventing that liquid from flowing. As soon as I lift this screen off, the liquid that was that forming that letter or number or character right here will start to spread. That exact same spread of liquid we talked about with the solder mask, where the surface tension of fluid wants to form that little dome, so it's going to want to spread out a little bit. We have the same thing here. And so historically, if I tried to make characters too small because of that spread of the ink, I would run into problems like the opening in the R would just merge together and I have a white blob, and so on. Newer methods exist that use direct printing, similar to an inkjet printer. The first generation of direct printing used old dot matrix style printing, where it put a dot, a dot, a dot, and basically at close up it was a bunch of dots, but at human readability distance, you could kind of see the character out of it. Newer machines are direct inkjet printing, and we'll see an example of one of those machines next week during manufacturing. In order to achieve good readability, a text ratio, a ratio between 5% and 20% of text height to stroke width, I should say, is recommended right here. So here is an example board that I actually got from Apex several years ago. And we'll look at them over here. So we said between 5 and 20%. 5%, so it's the ratio of the height of the character to the width of the line forming the character. So the smaller the ratio, the thinner the stroke is compared to the height. So in a small ratio character, large text like this 2 millimeter here or 85 mil here actually start to look a little too thin, almost like they're fading out a little bit, right? But as we go down in character size, for example, look at the 0.6 and the 0.5 right here, I can still pretty much make out the dot and the 5 right here of the 5.5 millimeter here. Same thing here. The 0 right here is definitely easier to determine that that's a 0. Here it became the white blob. And I can still basically make out roughly the letters MM right here in the 0.6. The 0.5, square, square. Whereas if we go to a higher ratio, much thicker stroke compared to the height right here, the same 2 millimeter high right here, but in this case, this now has that nice bold look, easily readable from a distance. But as I go down, the 0 right here, look at the difference. The 0 right here, I can still see the 0 with the line through it. Here I've got basically a white blob. The 5, unless I'm way zoomed in like that, is that a 5 or a 6 or a blob? What is that? That's a blob. My M's right here look like blobs. These are starting to look like squares and so on. So the ratio of character height to character stroke width is going to affect our readability. Additionally, we should be cognizant there's not much we can do about it, the design, unless we do absolutely zero routing of any kind on our outer layers. But when we do route characters over the traces on our board, even though those traces are covered by solder mask, there will be some irregularity in the character height or deformation of the character. For example, here, text over some traces right here. So squiggly traces and a straight trace right here. You can kind of see the crease happening in the traces right here, specifically in the E and the T right here, kind of blurred out a little bit here. So just be cognizant, you might see a little deformation in the way your character looks. That's just nature of a liquid. You're putting a liquid on a three-dimensional surface. It's going to flow and, not only in X and Y, but it's going to flow down the wall in Z axis. So you're going to get those little smears. A couple of other things here. Whoop. Wrong one right here. Didn't mean to click. I meant to try and do that. Exposed. So anytime there's an opening in the solder mask, exposing my copper below, as in the case of like vias or solder pads or anything like that, by default, unless you explicitly tell them not to, your fabricator is going to clip solder mask or clip the legend ink off of exposed copper so you have a solderable surface. Any legend ink left on a solderable pad like this will become a contaminant that will prevent or cause a defect in your solder joint formation. So by default, your fabricator is going to remove or trim the legend ink back from all of these exposed holes. You can also put text as copper. You can actually put text as a removal of solder mask. You can do all kind of other tricks with your legend ink and so on. So there's just a couple of things. But definitely wanted to talk about the ratio. That's a key one. And being cognizant of the fact that we want to make sure that our legend ink does not show up on our exposed copper that'll be our solder pads. Next is copper finish. Hopefully we're all familiar with Hassel or HAL, the hot air solder leveling. This is the surface copper finishes. These are the exposed copper where we want to have a solderable pad, like the plated through holes, surface mount pads for our components, vias if the via is going to have the solder mask open and so on. Again, we don't want to have any copper surface directly exposed to the environment. Otherwise, we go from nice shiny orangish copper colored to dingy green tarnished color where we can't solder or anything like that. So we need to protect that sensitive copper surface to do this, okay, for protection against corrosion. Hassel or HAL, hot air soldered leveling, again, where we dip the board. Now the Hassel works fine because we've already protected the traces, so they won't get any additional copper because of the solder mask, but only the exposed pads could get a little surface finish of solder directly on them, blow the excess off. We got that little skin of solder. The other second most common is ENIG, or electrous nickel immersion gold. IPC 4552 defines the requirements for the nickel and the gold layers of the ENIG process. Now, this is a debate I've gotten into multiple times with people from different industries. I say ENIG is the second most popular to hassle. And I've had people, especially from my mill aero class, say, no, ENIG is the most popular. And I would say that's true for certain market segments. For example, mill aero, where high reliability is critical. We're going to be building class 3 boards. High reliability is critical. Therefore, we'll probably do ENIG everywhere in mill aero, but they can afford it. When you take the electronics market as a whole, there's still a significant amount of the market that is either the ultra low cost consumer goods, think, the $2 or $3 little blinky toy for your kid with LEDs in it, the freebie giveaway swag from trade shows, the pens with the light up LEDs in them, or the fidget spinners that people give away. If you're giving away a product for free, you want to produce it at the absolute lowest cost possible. And the cost to do hassle is far, far less expensive than the cost to do ENIG. So taken as a whole, with all the low-cost product out there, especially in the consumer market segment, hassle is still the most common. Okay. PCB layout. Yes, Kevin, question.
Yeah. What about other finishes? Like, what would be the ranges for the fabrication processes, like in terms of the cost?
So there's two other finishes which I don't really bring up in this class. I do bring up in my mill aero, since it's being just a fundamentals. There are actually three other finishes out there. There's immersion silver, immersion tin, and then there's AnyPig. Immersion silver and immersion tin are effectively the same as the gold, but without the nickel layer, where they're still more expensive, and both the immersion tin and the immersion silver do have significant product producibility problems. Immersion silver is as corrosive as pure copper. It's a much lower cost alternative to ENIG, because silver is definitely cheaper than gold, and you don't have to put the nickel layer in, so it's half the process steps. But the silver now requires extra special processing care, and pretty much if you're going to do immersion silver, you want to go right from fabrication directly into assembly. So if this is like where you as the company are buying 1,000 boards and you're going to build 100 a month for 10 months, so you want to buy all 1,000 at the beginning of the year and then have them sit on your shelf in a warehouse and build 10 a month or whatever it is. The immersion silver, after the first couple of weeks, that silver has got the black silver tarnish all over it that needs to be cleaned and polished off before you can work with it. In fact, there's even special paper that they have to put between each board just so it doesn't corrode even any further. It has to be kept vacuum packed just like you would desiccated environmental seal bags for moisture sensitive parts. Immersion tin. How many out there have heard about tin whiskers? Yes, hopefully, yes.
Yes.
Tin whiskers is a phenomenon when you have ultra pure tin with no other metals alloyed in it, sitting all by itself, even with no other environmental forces, including no electrical charge. It will on its own grow little thin hairs of tin, looks like little hairs growing off of the part, and they will basically build a little lattice of hairs that'll basically short contacts and short points together. So immersion tin, again, much lower cost process than ENIG, but now you run into a tin whisker growth problem. So again, if you're going from fabrication and going right across the street to assembly and immediately assembling them, it's a fine process. Then the last process, AnyPig. The military guys are actually starting to look to AnyPig. It's a now even more costly process than ENIG in that it is ENIPIG, right? Electros nickel immersion palladium immersion gold. So it adds the nickel phosphorus layer. Then between the nickel phosphorus and the gold, it adds a palladium, yet one more precious metal layer. and I get into that in my mill aero class. It has to do with the intermetallic joint formation and structural integrity of the intermetallic crystalline growth layers between the nickel and nickel to gold is a good layer, but under certain conditions, it can fracture right along the nickel phosphorus to gold interface. So you make a second intermetallic bond, nickel to palladium, and then palladium to gold, so they get better structural strength out of those. But now we're talking two precious metals instead of one, plus instead of a 27 bath, it becomes like a 32 or 35 bath chemical process to apply, treat, neutralize, et cetera, over and over again. Um, we'll look at that next week during manufacturing. But yeah, I pretty much stick just to Hassel or Enig if I'm going to do one.
Would you know?
Yeah.
Oh, I'm sorry.
No.
Would you know what the like the cost difference per?
So
I don't know. Yeah.
Yeah. So Hassel, dirt cheap, pretty much included with standard fabrication costs, no real cost adder. Uh, immersion silver, immersion tin. I will tell you, my data is about 15 years old. The last time I did one of those, and I got burned on them. That's why I don't use them anymore. It was about, I want to say, at the time, this is like 2010, 2008, 2010 time frame. Was about a 10 or 10 to 15% cost adder to the board to go to that process. Maybe 5 to 10% for those two, and like a 10 to 15% cost adder to do the Enig at the time. So whatever you would have paid with Hassel, you pay about 10% more to do Enig and about 5% more to do immersion silver, immersion tin. Again, old data, and part of that comes down to the fabricator you choose, right? So there's no one right answer on that, because if you have a fabricator, and I'll use Summit Interconnect, I know them quite well. I'm friends with the VP of technology over there. Uh, they specialize in military applications. They do Enig day in, day out, all day long. It's become second nature to them. So for them, the Enig process is not as special, so they can do it at a reduced cost. If you're going to a fabricator who primarily does Hassel, like low-cost consumer goods all the time, say, yeah, we have an Enig line, but we don't use it that often. So for them, there's a bit more engineering setup, making sure everything's working right, etc. So they're going to charge you a little bit more, and so on. So it really comes down to a question of, depends on your fabricator how much more they want to charge you for the Enig versus the immersion silver, immersion tin. In fact, the immersion tin and the immersion silver have actually gone enough out of favor that a couple of fabricators said they even removed their lines altogether and said, yeah, we go out of shop to that. We go to a larger board shop, and we just say, hey, can we run our boards through your immersion silver line, because we got a customer that says they want it, kind of thing. So again, it's all going to be determined by which fabricator you use as to what your cost adders are going to be. But in general, immersion silver, immersion tin are going to be about half of the cost adder of Enig, and then but all three of those are going to be a bit of a cost adder over the standard board fabrication, but not a huge cost adder.
Thanks.
Okay. So general slide here just says, PCB layout engineers should consider all these different properties when defining the optimal structure for your design. And just an example, I used high reliability, so mill aero board, right? A high reliability guy might say, I want a minimum of 2 sheets of prepreg per layer, whereas a high volume consumer guy might say, I want the lowest cost option. I'm willing to go with a single thicker sheet just to keep my cost down. Similar trade-offs can be made on surface finishes, solder masks, legend inks, etc. We just talked about the surface finish one. Kevin, great segue for me there. Some of the trade-offs we were talking about between immersion silver, immersion tin, Enig, Hassel, and so on. Idea there. Okay, the last section here on, actually, I take it back. We got 2 more things of materials we're going to talk about here, although it's break time. Why don't we take a short break today? Let's take, like, I don't know, 6-ish, 7-ish minutes. Be back at the 10-minute mark. I'll stay online if there's any questions, but I do want to try and get through the last of these slides here. We have about 20 more to go. And then work on this week's assignment a little bit. I can stay a little bit after class day, but just not super long if we want to go into the coursework a little bit as well. All right. See everybody back in like, yes, question, vibes.
Yeah, I was wondering if now would be a good time for me to resend that email for the Altium IPC.
Yeah, just send it to those same two that I dropped in the chat.
Okay.
Yeah.
And I was wondering, I don't know if I missed it in the beginning of the class like a couple weeks ago, but are these slides available online?
No. Yes, there was a statement made, and no, they're not available. It's an IP thing, an intellectual property thing with IPC. At this time, we are not able to give the slides out. I did make a statement that says, come back, watch the recordings, and make notes for yourself of these. It's one of the reasons why you'll often see me pause on a slide for a little while, so that way you can go back and freeze frame it and make notes for yourself.
All right.
But yes, at this time, we are not able to provide the slides in a PDF form.
No worries. Thank you.
Yeah, I personally would love to be able to give them out, but it is a thing that we're not able to do right now.
But you can give them out in the videos, correct?
The videos are, you will have access for a year to the videos up on our Edge page. So you can, for the next year, you'll be able to come back into the IPC Edge page and get access back to the videos and rewatch them as often as you like.
I had a question. If it's a good time.
Sure.
So you were saying like anywhere between like 0 to 5 to 10%, maybe even 15% cost adder for the surface finish. What are some other big hitters that can, increase your cost of your board significantly that maybe designers should be looking out for?
Sure.
And
So I don't
optimizing?
normally go over cost in this class because I'll qualify this, but we'll talk some generalities here. Costing is a very subjective, based off of your company, what agreements and arrangements you have with your fabricator. Items that might be a cost adder for a small company are just say, the fabricator says, oh, you're a preferred customer of ours. We're going to waive those extra fees for you and just do it at our cost, or things of that nature. So costing, I usually say, talk to your procurement people. They will have agreements and arrangements with your vendors and so on. But in general, the big hitters are the process. Every time you change process complexity. So one of the biggest cost hitters in board design, the minute I change from a standard double-sided board like we used to do back in the 80s and 90s and started doing multi-layer, right? So the processing of a simple double-sided board to now processing multi-layer boards, that was like a 50 to 75% cost adder right there just to move into the multi-layer process. But once I'm in the multi-layer process, each additional pair of layers, because we're always going to add layers to our board in pairs, never single layers, always going to be an even number of layers in our boards. Now we're talking in like a 2% cost adder for each additional pair, right? So it becomes almost negligible if I want to change from 8 layers to 10 layers, 10 layers to 12 layers, and so on. Right? So there's a big cost adder jump from double-sided to multi-layer. There's a big cost adder jump from standard multi-layer to sequential multi-layer, right? Which you might have to do if you're doing HDI with micro vias and so on. So second big cost adder right there. Okay. You can then also, there are cost adders. Another big one that is going to be, and this is one that's going to be fabricator dependent. So if I go up over here, I did that. Oh, wrong one. Didn't mean to do that. Meant to this. Yeah, PCB, some interconnect. Okay. So each fabricator is going to have a list of standard technology capabilities here. Ooh, that's actually an interesting one. I'm going to leave that one up there and come back to that one. We'll go over here to the PCB capabilities. So this particular vendor, Summit Interconnect, they're one of the big vendors here in the States. I'll actually come back to that later. All right. So we're going to look like over here, etch features, right? Inner and external layers, print and etch. They have what they call standard technology, advanced technology, and emerging. And then it's going to be based off of copper weight. So if you do a design with 1 ounce copper layers on your inner layers, they're basically saying the minimum feature size is a 5 mil trace width and a 5 mil trace spacing. That they can do all day long, no real cost adder. You start trying to do, you say, hey, I'm doing 1 ounce copper, but I really need to do a 4 mil trace or a 4 mil space. Okay, you've just jumped into their advanced. That's a cost adder. You've jumped all the way into emerging, significant cost adder, right? You're basically going to have higher scrap rates. Another big one is going to be board or manufacturing panel yield. We'll talk about this more next week, but effectively, whenever we fabricate our boards, the fabricator is using a standard panel size, usually 18 inches by 24 inches. And if your fabricator, right, if you design your board in such a way that because of the size of your board, they can only get one image of your board on that 18 inch by 24 inch panel, and we'll talk a little bit more about this next week, is that the fabricator needs some room around the perimeter of that panel in order to put their like test features that prove that they produced it correctly without damaging your boards and so on. Basically, there's going to be a set cost that they have to produce that panel. Maybe it's like $3,500 or $5,000, whatever it is. Let's go 5,000. The math is easier. If you design your board in such a way that because you made it just a hair too large that they can only get one image up on that panel, you're paying $5,000 a board because you're $5,000 a panel. If I can get 2 images of that board on the panel, because I shrink the board size a little bit and they can rotate 90, you get 2 of them next to each other on that panel, each board cost me $2,500. I still paid $5,000 for the panel, but I got 2 boards on the panel, so each board is $2,500 and so on. So optimizing the panel utilization and getting your boards, the shape of your board to fit on their panel, what we call a min for max, the minimum price for the maximum number of boards, how many boards they can fit on the panel, that's going to be a cost adder. The material selection, right? If you say, I need some exotic material in my board, that's going to be a cost adder versus if you're using, generic materials that they have in stock, no cost adders. So those are several of them, right? So all these manufacturing process steps that we're going to talk about next week, if you stay within the standard capability, no real adder. The big cost adders are going to be things like this, where I push into advanced or emerging technology capabilities at the fabricators. Does that kind of answer your question?
Yes, thank you. I was just curious, the panelization that you mentioned, is that usually listed?
There's no one right or wrong. The panel sizes are known. The panelization is something that you have to figure out.
Right, that's what I meant. I guess the panel size, like the min or max.
The fabricator will typically tell you what their standard panels they keep in stock are. And if they don't listen to the capabilities, you just call them and say, but in all honesty, if you stick with 18 inches by 24 inches, at least here in the States, that is the bread and butter that everybody does. There are some other panel sizes smaller than that, and if you need to go larger than that, you go over to mass lamination facilities where you're paying extra money to do extra large panels. But if you assume 18 inches by 24 inches, you're good to go. Okay, let's quickly run through these last couple of slides here. Hopefully everybody's back from break. We actually went over a little bit there with a great question there. So we're going to talk solders and fluxes. Solder and flux will also need some special consideration. Solders are alloys that are designed to melt at specific temperatures to form a metallic bond between the component termination and the PCB solder pad. The bond serves 2 purposes. First, it creates the mechanical connection of the components of the PCB, similar to a weld in a mechanical assembly. And second, it creates the electrical connection. From IPC J standard 005 is going to define the requirements of the solder pastes used for SMT designs. J standard 006 will define the requirements for the solder alloys themselves used in traditional through-hole designs, as well as ground up to become the solder powder that's used in the solder paste. From J standard 006, the solder can be produced in several different forms, including bar solder, wire solder, ribbon solder, powders, spheres, and special. Bars are basically large ingots of solder that are melted in big solder pots used in traditional wave soldering machines. Wire solder, we've all used this, hopefully. That's that spool of wire, looks like a piece of ribbon or a little, round cross-section wire that you pull off when you're doing hand soldering with a soldering iron. Ribbon solder is we don't see that used much anymore, but back in the day where designs were primarily through hole and assembly was done by technicians sitting at a soldering bench all day long, just soldering parts into boards, old school computers and stuff that were all through hole parts. Ribbon solder, you take the wire solder and you flatten it out so it has a broad, wide, flat section. This was just a way to get an increased volume of solder in less amount of time because you didn't have to feed as much in as quickly. Powders are the microspheres or particulates of solder used to make the solder paste. Spheres themselves, defined as spheres, are special types of powder that are larger in size and always spherical in shape, and these are used typically in the BGA packages. And then finally, special. These can be any custom shape we want, such as solder preforms used to add extra volume to solder paste if it's a large pad on a certain amount part. Think like a D pack or D squared pack solder tab. Alloys. There are numerous different alloys defined in J standard 006. These include both traditional tin lead solders as well as lead-free solders. As mentioned, the traditional solder alloys are a mix of tin and lead, and the alloys are defined by their constituent element percentages, with the largest percentage first, and the next one second, and so on. The ratio of tin to lead is going to determine the melting temperatures. Additionally, there are some formulations that have hysteresis in the melting temperature, and some that do not. The melting temperature of solder has two defined temperatures. Solidus, which is defined as SOL, is the temperature at which the solder turns from a liquid into a solid, and liquidus is the temperature at which the solder turns from a solid into a liquid. Basically, liquidus is the melting temperature and solidus is the hardening temperature. For the ones with hysteresis, there's typically about a 10 to 20 degree F spread or hysteresis between these. However, if the alloy is formulated in such a way that the solidus and liquidus temperatures are the same value, the solder is said to be defined as eutectic, and one of the values in the table will be defined with a lowercase e instead of a numerical value. In addition to the other elements besides tin and lead, the solder can change. The addition of other elements besides tin and lead in the solder can change the performance of the solder for specific applications. The first formulation or the first additive alloy was antimony. Antimony-containing solders were done to prevent a condition originally defined as tin pest, not to be confused with tin whisker that we just talked about, but tin pest was a phenomenon where ultra-pure tin undergoes an allotropic transformation at very low temperatures from its metallic crystalline form, its shiny metal metallic crystalline form, it turns into this white powdery substance at very low temperatures. This was originally thought to be a degradation of the performance of the tin and was a concern, so they started adding antimony. However, it turns out that any other metallic element alloyed with tin also mitigates this tin pest problem, and therefore, like the lead that's already in tin lead, therefore it was not necessary. The antimony-defined alloys are still available for legacy products, such as military applications, that were built, tested, and qualified with the antimony solders, and therefore the military says, we qualified it with antimony solder, you shall use antimony solder, even if we have to pay extra for it. So it can still be produced, but in general, it's not used anymore. Bismuth-containing alloys. These alloys are designed for ultra-low temperature soldering application. Bismuth is also used to enhance mechanical properties of solder joints. So it makes a stronger solder joint. However, when alloyed with lead, bismuth changes the solidus and liquidus temperature so low that it can actually be done at room temperature or just slightly above, slightly elevated temperatures. Cadmium-containing alloys. Cadmium-containing alloys are useful in EMI and RFI shielding applications. However, cadmium is an extremely toxic and carcinogenic element. Therefore, using cadmium-containing alloys should only be used when no other option is available, and appropriate PPE should be used at all times when handling and processing cadmium alloys. I say EMI RFI in certain applications, especially in RF or certain high reliability military applications for extreme EM environments. Standard solder joints, even though it's a completely metallic connection, still provides a path for some EMI RF radiation to pass through, and so using cadmium containing alloys can help further reduce EMI RFI. Again, great stuff, very nasty, very toxic. Use as a last resort. Copper-containing alloys. Copper was added to tin lead alloys to reduce tip degradation in hand soldering. Again, this is back in the day when the majority of commercial soldering was done by humans, technicians at a soldering station with a soldering iron, and they were just soldering day in, day out, all day long. So anything you could do to get more life out of your soldering iron was considered a bonus. So adding copper to tin lead. Copper is also now one of the primary elements used in lead-free solder alloys. More on that in a minute. Gold alloys. Ultra-high purity gold alloys are used in barrier-free die attachment applications, basically wire bonding applications where you have to melt a gold, if we have to melt a gold wire directly to the crystal, the silicon surface of the pads of the silicon die, doing direct die attach. Standard gold alloys are also used in high reliability hybrid applications and are used in microwave frequency applications. Again, there's certain properties of the conductivity of gold that's better at the microwave applications than the standard tin leads. So we'll use that there as well. Finally, indium-containing alloys. Similar to the gold-based alloys, indium-containing alloys are used when soldering to gold surfaces and in application at microwave frequencies. Unlike gold, however, indium alloys work at low solder temperatures, below 120 degrees C, and in lead-free alloys, indium also acts to enhance mechanical properties similar to bismuth in tin lead joints, and so on. Okay, from JSTAR 006, the designation for the solder alloys. For tin lead alloys, the names are named off the chemical symbol and percentage amount, such as SN60 PB40, which is 60% tin, 40% lead. SN63 PB37 SB0.4 is 63% tin, 36.6% lead, and 0.4% antimony. So the 37 here was 36.6. It was a rounding, so we didn't do 36.6 here. And so on. So you have to look at the table to know where the rounding is coming from. And in lead-free alloys, the name is based on an abbreviation of the elements in order of concentration and the percentage value of the elements except for the tin. The form is typically SAC XYZ here, where the first three letters are the elements, such as tin, silver, copper. So the S, the A, and the C give us SN, AG, CU. So SAC. The first two numbers, XY, are the percentage of the second element in x dot y percentage, and the third number z is the percentage of the third element in 0.z form. So as an example, SAC 305 is 96.5% tin, 3.0, so the 30 is 3.0% silver, and the 5 there gives us 0.5% copper. We add those two together, subtract from 100, and the remainder is our tin right here. Okay, now that we've selected our solder alloy itself, next we have to pick flux. So in addition to the solder alloy, the flux formulation must also be carefully considered. Fluxes are materials that have two main uses. The primary is to remove oxidation and contamination from the surface prior to soldering, and the secondary purpose is to provide improved or uniform thermal energy transfer from the heat source to the solder, the terminal, and the pad all at the same time. So anytime I have a liquid, liquids work much better at uniform thermal energy transfer than trying to put two solid surfaces together due to the micro imperfections of the solid surfaces. Flux is going to be classified by 3 parameters: the flux composition, the corrosive activity level, and the halide content. Table 1-1 from J-004 defines the flux identification system. There's RO for rosin, RE for resin, OR for organic, IN for inorganic. Within each flux composition, there are 3 activity levels: low, moderate, and high. And within each flux activity levels, there are 2 halide content levels, the 0 and the 1. So we take these 3 together, the L, M, and H, along with the 0 and 1 for the halide content, along with the first 2 letters right here, gives us our full flux designation: ROL0, ROL1, etc., all the way up to INH1 right here. The flux composition has the 4 types: rosin, resin, organic, and inorganic. Rosin is natural rosins extracted from olear resin of pine trees, basically pine tree sap. Purified and processed pine tree sap actually turns out to be a really great surface cleaner and uh, uh, preparation for our solder pads. Resin is simply lab created synthetic form of rosin flex. And then organic and inorganic are both natural rosin fluxes, but with additional acids added. Organic, we add additional organic acids. Inorganic, we add additional inorganic acids. For the inorganics, this is usually either hydrochloric or phosphoric acid added to the rosin. Organic and inorganic fluxes are primarily used in high contamination environments where large amounts of surface preparation are necessary, and typically not used in electronics manufacturing. After the flux composition type is selected, the activity level needs to be considered. Low is low or no flux or flux residue activity. Medium or moderate is medium flux or flux residue activity. And high is high flux or flux residue activity. So even without the additional acids, the flux itself becomes acidic in that it is stripping away surface contaminants. This is one of the reasons why we don't want to use the organics or the inorganics. We'll use organics or inorganics if it's like a big, large, massive copper feature. Think copper piping, or think like 2-inch square copper lug bars for connecting, to mains power in our, three-phase wiring coming in for the mains lines coming off of the transformers, or things of that nature, where I have enough material. If I'm talking, printed circuit boards, my copper is only, 1 mil thick or half a mil thick, 1 ounce and half ounce copper. If I start putting those highly corrosive material on there, I'm just going to dissolve my copper completely off the board. So I use that. The specimen, just to look at the activity level, even without the additional acids. Low activity, when placed on our copper specimen here, we have slight surface degradation right here, but no actual breakthrough. Medium, we start to get pinholing, and with high flux activity level, if left on the copper, it will completely eat through the copper all the way through the board right there, or all the way through the copper feature. Finally, after flux composition type and activity level are selected, the halide content level needs to be considered. For all 3 activity levels, the level 0 halide content requires less than 0.5% by weight of halides. For the level 1, the halide content rating, the percent weight allowed, is dependent on the activity level. So for low, it's going to be between 0.05 and 0.5. For medium, it's between 0.5 and 2%. And for high, it's greater than 2%. Again, table 3-2 and J-04 list the activity levels. The halides are the ionic contaminants. It's the halogens, which I can never remember them all. It's like, I think it's like iodine, bromine, and so on. There's like in the periodic table, there's one column which are the halogens or halides, and they're the ones that leave the ionic contaminants when they're left on the board, the salts and so on, that can be the conductive paths, which we don't want. Okay, for modern electronics manufacturing, where PCBs are assembled into PBAs very soon after the PCB fabrication, or where PCBs are stored in controlled environments prior to assembly, the use of the M and the H level fluxes is not recommended. Additionally, it needs to be noted that the L activity level only describes the residual corrosive behavior of the flux. While these fluxes are listed as no clean, this only means they will no longer corrode the conductive features the way M or H level fluxes will, like we just saw. these fluxes still contain many ionic contaminants that can cause conductive paths between features on the board. Okay, so if your design is for a high reliability application, such as medical, aerospace, military, etc., it may still be necessary to thoroughly clean the flux residue off the assembly before installation into the product. And I should put the flux residue off of the assembly. So even if it's not going to be corrosive to the copper, it can still provide that conductive path, which could cause degradation of the performance or failure of your product. For consumer goods or kids' toys or whatever, if the blinking lights on your kids' toys stop working over time, it's not the end of the world. On the other hand, if we're in a war zone and we're relying on that shoulder-launched missile to take out the enemy's equipment, that thing better work the first time, every time I push the button. I don't want it to suddenly stop working after I've been in the field for a while. So depending on the reliability requirements, it may be necessary to have removal, even if it's listed as a no clean flux. Yes, question out there.
Yes. I'm glad you pointed that out, because that's been a problem of mine for many years, is trying to convince my company that it's worthwhile to clean our boards.
Because they're using no clean fluxes?
Yeah, and so the boards go into the PCBA testers, and it doesn't take long for the residue to build up on the pins, and it doesn't work anymore.
Yep.
And they're calling me to fix it, and it's been an issue, and so I'm glad you mentioned that. I appreciate it.
Yeah, no worries. Yeah, take the notes back to your boss and say, like, look, even the people
Absolutely.
at IPC tell you, it's like, look, no clean only means it's no longer corrosive. It's still ionically contaminated.
Yeah.
Wash that stuff off.
And the other statement that I've been told, which I'm not sure is true or not, is that we're going to obtain a wave soldering machine, and somebody in production had mentioned that it's going to take care of that problem for us.
No, it's not. It's going to put even more on. The way wave soldering works, they literally spray the entire surface of the board with flux, then it goes through the thing. You got to wash it more after wave solder than you do after reflow solder.
Okay. I just wanted to get some backup from the experts.
Yeah. Yes, the way wave solder machines work, literally, if you ever watch a video of a wave solder machine work, the very first stage is the board's coming in. They literally have a mister spraying the entire surface of the board with flux. Then they have you go through the thing of molten wave of solder, and the flux helps the solder wick up through the holes because it's traditionally meant for through hole. Then when you get out, then you absolutely have to go through wash because the entire board's sticky with flux.
Yeah. Okay. Thank you. I'm gonna bring that up to the uppers. Thanks.
No problem.
Make my life a little easier.
Yep, no worries. Awesome. And Kevin, it looks like you had a question out there as well.
Yeah, I was wondering what time frame are we talking from the time that you leave the flux on there that you start seeing those holes and stuff that.
It depends on the activity level, and I've had a board once where somebody used high activity, and it was the next day. We got basically it was overnight. It through it. Sometimes it's even faster than that. It's also going to depend on the size of the feature, what copper weight you're using. Are you using 1 ounce, 2 ounce, half ounce, quarter ounce, etc. But it's pretty quick.
Wow. Okay.
Yeah. All right, great questions. Okay, solder paste, J7005. We'll go through these here real quick. I might skip and maybe refer back to it. I've got some stuff about conformal coatings. We might skip that and come back to it because we're going to talk conformal coatings again next week during manufacturing. So I'll probably skip that so we get some time today on the board itself. But we'll go through the pastes here real quick, and we'll go. The designation for solder pastes. In addition to the solder alloy, the solder paste also needs to define some additional properties such as what flux is used, the powder type and size, the metal content, the viscosity, the unit package size, and any other specific characterizations necessary. Solder pastes are an emulsion or an amalgamation of solder powders defined from J*006 with a flux defined in J*004, along with some additional binding materials to form a paste. The binding agent and flux are consumed or burned off during the soldering process, leaving a residue that must be mitigated or cleaned at the end of the assembly process. Proper selection of solder paste is critical to successful SMT assembly process. Due to the emulsion process, the solder paste must be refrigerated when not in use. Just like peanut butter at home or Italian or vinaigrette salad dressings, you leave those in the bottle for a long time and the oil separates up to the top and the rest of the stuff is at the bottom. You got to shake it back up. The same thing happens here. The fluxes and other binding agents will eventually separate from the solder particles and you will no longer have a viable solder paste. You'll basically have a goop that doesn't work right. So just like with vinaigrettes and other oil-based emulsions, you must keep them refrigerated when not in use to help keep the viscosity of the oil thick enough that it stays emulsified like that. And additionally, solder pastes also have a short shelf life. Unlike bar solder or wire solders, I've got a spool of wire solder in my electronics kit, 30-something years old now. I had it when I was in my 20s. Yep, a little over 30 years old. Got it in my early 20s when I first started going to electronics school. And that still works to this day. I can still solder with it, no problem. However, solder paste, because this emulsion processing here, they typically have about a 6-month shelf life. Now, again, this is not something you as designers typically need to worry about unless you're also ordering some to keep in your own labs. Make sure you have a fridge you can keep them in and make sure that you replace them every 6 months, so don't buy in large volume. The shelf life, that is something that your assembler will typically need to worry about, but typically not you as designers. One of the key areas of concern when selecting solder paste for use in an application beyond the alloy formulation is the powder or particle size. Table 3-2 in J*005, the larger the type number, the smaller the powder size. This is important when placing small SMT parts in the design. If the solder paste stencil opening is too small, the larger powder size will not easily fit into or release from the stencil. We'll talk about this again next week during manufacturing, but effectively what we're going to do is have this aluminum or steel sheet of metal that has laser cut openings in it for each surface mount pad. We'll then put the solder paste in a bar like toothpaste, and the squeegee will squeegee it through and squish it through the metal stencil so it properly applies the solder paste to each and every pad that needs solder paste applied. But as my parts get smaller and smaller, the size of that opening obviously is going to get smaller. The opening for an 0201 resistor is significantly smaller than a 2010 or a 1210 type of resistor. So if I try to use a older solder paste that was meant for those larger pads, it's not going to, literally the size of the powder particles is not going to easily fit in there. And what do I mean by the size of these particles? I'm assuming almost everybody out there enjoys a good cup of coffee with me in the mornings trying to wake up. Yes? No? Everybody out there? Anybody out there not a coffee or tea fan?
Love the stuff.
Negative.
Exactly.
Negatory.
Yes, we love our coffee, right? How many of you out there grind your own coffee beans at home and are as much of a coffee snob as I am to actually buy whole beans and grind them yourself when you need to make your cup of coffee?
That's me.
Uh-huh. And so for those that grind your own coffee, no matter what kind of grinder you're using, whether it's a blade grinder, a burr grinder, or anything else in between, crushing it by hand in a mortar and pestle, you always get, right? Burr is always the way to go. You are correct, Vibe. Burr is always the way to go for grinding. That's what I have. But we also know that even after we grind it, the majority of the powder is the size we wanted, but there's always some pits in there that are a little bit larger, some that are a little bit smaller. The same thing happens here. We're going through a similar grinding process. So from this table, which looks a little confusing at first, What we are going to be concerned with primarily is this 80% minimum between number right here. So for type 1 solder powder, 80% of the particles or the powder in there is going to be between 75 and 150 microns in size. 10% of the particles are going to be less than 75. 10% are going to be between 150 and 160, and less than 0.5% are going to be greater than 160. So basically, this is the primary range with a few ground bits that are too big and a few ground bits that are too small. So as we can see here, type 1 is 75 to 150 micron in size, where type 7 is between 2 and 11 micron in size. This is all given in microns over here. Okay. Now, couple of things to note, and I actually just learned this myself recently from one of the equipment vendors last year when I was at the big Apex trade show, which I highly recommend everybody come to. And that is up through type 5, easy to process. But once you get to type 6 or smaller particles, they often have to process them in an inert environment, nitrogen or other inert gas environment, because the powder becomes so small that the materials can start to oxidize and break down in our atmosphere or run into other problems. So I don't know if that's true for all equipment vendors, but it is worth a discussion with your assembler on that. Okay. But anyways, again, most of the stuff we're doing in modern electronics, the type 5 is more than sufficient, the 15 to 25 micron powder size right here. Okay, so we're going to stop here. We'll pick up. I'm going to add these slides to the slides we would normally have next week on manufacturing, because we're starting to talk about conformal coats and CT mismatch during processes here. I do want to spend a little bit of time working on the board itself. So while I'm pulling up the board file here, are there any last questions on the materials that we just went over today?
What could be a good practice to clean the flux?
So there's two primary practices. We're going to talk about those next week. There's aqueous wash and solvent-based wash. You can do ultrasonic or traditional. One of the most classic ways to wash it is basically an industrial dishwasher. It literally has a pull-out rack, just like your dishwasher at home. You'll stack the boards in it like they're the dinner plates, and it goes through and it uses a deionized water with a saponifier, basically a soap, that basically dissolves the material off, rinses it off, and you go from there. That's assuming that all the parts on your board are capable of going through an aqueous wash. Some parts are not, such as like mechanical switches. There's ultrasonic washing. There is ultrasonic submerges in a tank, kind of like for cleaning jewelry, where there's an ultrasonic vibration that causes the fluid to flow under the parts and so on. You can do solvent-based or water-based cleaning and so on. And that is actually a discussion to have with your assembler, because the honest answer is there's no one right way. It's going to depend on the type of parts you have on your board. Do you have BGAs? Do you have BTC parts, the bottom termination only parts, right? Such as QFNs, DFNs, where the solder is on the bottom surface and there's no height off the board. Do you have a mix of through hole and surface mount? Do you have any sensitive parts such as mechanical switches or push buttons or things of that nature that can't go through a standard aqueous wash? So depending on the type of parts you have and the technology of those parts, there'll be different best practices based off of your design. So that's a discussion to have with your assembler. Yes, Kevin.
These aren't like notes that go on your fab drawing, right? These are like process steps that are
Actually,
negotiated
it's a note
outside of
that
that.
yes and no. So we'll see this when we get to documentation, not on the fabrication drawing, but on the assembly drawing. There is an actual cleanliness designator that will say this board must be washed and I want this level of testing. I want you to test and prove that there's no surface ionic contaminants left, there's no surface insulation resistance increase or anything of that nature, and so on. Decrease in surface insulation resistance, no ionic contaminants left, where yes, not only are you telling them to wash it, you are telling them what level of cleanliness you expect of your board after the fact. So those are notes we're going to put on the assembly drawing. Now, as to whether you need aqueous wash versus ultrasonic, that's usually a process that I'm going to leave up to the assembler, with the exception being what I will typically do is either on the assembly drawing or as part of the assembly drawing, the parts list, I will indicate if there are any specific components that cannot be aqueous washed. And oftentimes what we'll do is say, okay, I want to keep my cost low, so I want to be able to go through aqueous wash. I have some mechanical switches on here, so I'm just going to tell the assembler, hand assemble, hand solder these 5 switches onto the board because they're through hole after the board's gone through the regular washing process. That way they only have to do a local cleaning of those couple of solder pins. So yeah, these are all decisions and notes that we will put on our drawings, but it will be the assembly drawing, not the fabrication drawing.
Thanks.
Yep. Okay. Great. So let's take the last 15 minutes here. So we left off last week, I believe we had a chance to look at, we created the board project, we did our updates, and then we brought our design forward. And so we have this stack of parts over here. Now, for those that are new to this class that did not take my PCB1, I am taking advantage of the hierarchical structure of the schematic. So for example here, so for all those who come back from course 1, you've seen this already. We've talked about this already. And we may have talked about this a little bit last week. Kevin and those that are new, please watch the previous videos to see how, as well as once you get access into the Altium 365, how to clone the starting point project and get to this state we're in right here, and so on. But over here, so if we look at this top page of my schematic, and let me go also do this. Let me pull my messages panel back down here, so I have more room to work over here. So I have this top page right here. This is almost like a block diagram level. And for example, I wanted 16 LEDs in my design, and I want them to be independently addressable. And I'm assuming I'm going to use bicolor ones, so I've got a high and a low, so I can turn it, red or green or orange, red, green, back, forth kind of thing. Even though I didn't draw the symbol that way, but I've got both the high side and the low side addressable back to my FPGA. But rather than going to my LED page right here and drawing all 16 LEDs independently, I drew one LED circuit right here, and at this top page, I used the repeat command in Altium right here. And again, for those that are new, if you're interested in how I did this, shoot me an email. I'll be happy to do a one-on-one with you to explain this. But just I'm just giving you a high level here. I took advantage of this idea here of the repeat command that basically said, give me 16 exact copies of that LED circuit. And what that does for me when I bring the parts in, rather than just dropping all 16 LEDs with all of their resistors in one big block right here, instead, I now have this right here. We have what are called rooms. Each instance of that LED circuit becomes this thing here called a room, this little salmon colored box right here. Now to move my parts around. First, I'm going to be able to select my part. I'm going to click on it here and select my part, which real quick, up here under the gear icon. I highly recommend it if you are new to Altium and have not done this before, or if you've used Altium but didn't know about this one capability here. If I go up here to my gear icon, under the PCB editor right here and under the general, this option right here that called display pop-up selection dialog. Check that box to enable that capability. And now when I'm trying to select something, when I single click to select, it's always going to pull up this dialog so I can pick the feature I want rather than trying to hold in shift and click through things and click, no, I didn't want that. I didn't want that. Oh, there, now it's selected the thing I want. So if you're new to Altium and are not aware of that, I highly recommend you enable the pop-up selection dialog. I'm going to select my part. Now I'm going to click and hold so it'll grab it. Now I'm moving it around. My space bar is going to rotate in a counterclockwise, Shift plus my spacebar will rotate in a clockwise. And my letter L key, the letter L for the word layers, is while I'm moving the part around, the letter L is what will flip it to the bottom side. I'm then going to rotate this around. And I'm going to snap this so it's on center right there. Also note, and I think I showed you guys all this before, but over here with nothing selected, the properties panel over here shows me the general configuration of this board design. Couple of things I'm going to do if I scroll down in here, all the way down here to the bottom. This is where I can choose whether I want to work in metric or English. I've got mine set up for English, so mils. If you're more comfortable working in metric, you can choose metric right here. Additionally, I've got some selection filters up here. Right now, I have all the selection filters turned on, but you can turn these off and say, I only want to select pads, or I only want to select tracks, or traces, or vias, or polygons, or whatever, right? So you can say, I'm not going to let it select anything except one feature. I can also have snap options. I want to snap to grids, guides, and axes. I also want to snap on all layers rather than only on my current layer. And then for my snapping options right here, I enabled everything. Arc centers, track vertices, pad edges. So I just want all of my snapping capability turned on. I take advantage of that. There's some times where it gets in the way and I might go back and turn it off at times, but for now I want it turned on. Okay, so I'm going to place my two parts. I'm going to place my resistor on the bottom side of my board directly underneath my LED right here. I'm then going to go ahead and route. And I'll route the first one. So I'll go into my router mode right there. So Altium has now this floating toolbar up here with route and different features right there. If I don't want to get to it from the floating toolbar, I can also go up under the route menu and just say interactive routing right here, or I've got that mapped as Control W. Okay, so I'm in routing. Now, depending on the layout of your keyboard, if you're using a laptop and you do not have a keypad, you'll have to do this a slightly harder way. We'll go over that next week. I'm going to assume everybody has the number pad next to their keypad, right? So if you have the number pad, what I'm going to do is, first off, all of my available layers are down here on the bottom. I'm currently on my top layer. So I'm going to click right there in the center. And you'll notice there's my trace width. And I'm also going to note that hitting my shift key is going to flip. See how I'm doing the 45-degree angle, but see here how it's trying to go vertical angle first and then the horizontal part of the line? If I hit my space bar, it flips the other way. It tries to go horizontal first, then vertical. That's going to help me. The other thing I can do is, while I'm routing, shift plus my space bar will cycle through my different corner modes. A 45-degree radius, a 90-degree corner, a 90-degree radius. This option here called any angle, which is I can now go in any direction I want, or finally back to my standard 45-degree angle. I prefer the 45-degree angle, so that's what I'm going to use. I'm going
Is
to
the any angle, sorry, is the any angle same as the gridless routing that we talked about before?
The gridless routing works regardless of the angle mode. The any angle is more just like if you're doing an oddball shape, like a board shaped like an octopus or a star, or, whatever, and you've got parts placed at like 22.5 degrees from, from whatever, from nominal, right?
Gotcha.
So yeah, you want to go in strange angles, you can do that. But for normal routing, like we just talked about with the control impedance, we're going to try and have one layer primarily horizontal, one layer primarily vertical. So the any angle kind of mucks with that a little bit. So I try to stick to the 45-degree. It's a good, good bread and butter one. I've used the any angle occasionally for special cases, but for the most part, no. Okay, so I'm going to come up here. I'm going to click once. You'll notice that my trace has become solid there now. Okay, and now what I can do is my plus and minus that are in the number pad, not the plus and minus over the, next to the backspace up at the top near the function keys, but specifically the ones on the number pad. If you have a number pad, the minus will cycle backwards through my layers. So from top, it'll go to bottom, then from bottom to layer 9, from 9 to 2 and so on. Now it skipped 9 because remember last week we set up the rule that we were preventing the layer of we were preventing the layer of the digital from routing on layers 1 and 9, right? So I can go through my layers and set to whatever layer I want. I'm going to go back here. I'm also going to hit my tab key with any action you're doing, whether in schematic or layout. Hitting the tab when you're in an action pauses your action. I'm also going to come over here, and right there you can see my via diameter and via hole size. Right now it's set at the minimum, which I don't want. Remember, I want that nominal 35 with a 15 mil hole. Right there. And there, now I have my proper via size. I'm going to click once to place the via, and now I'm routing on my bottom layer. And now you can see I'm going to bring my trace back in there. Okay. Now I have the two signals down here, the high and the low side of the LED, but they end up going over to my FPGA eventually. So what I'm going to do is I'm going to click over here on the blue one, and I might just come down over here for a moment, hit my minus key to come back up here to my minus, to my top layer. And I might come over here and click this one and go over here and hit my minus key to go back down there. Okay. Now what I'm going to do is I'm going to click on this room area definition right here, and I'm going to find these little white handles. When I change from this 4-way crosshair to the 2-way, I can resize it. I want to resize this room such that it completely encloses all copper features. So I'm going to make sure I go there, and I'm going to pick this top corner right here. And I'll make something like that. Now here's the cool feature why I'm using the hierarchy. Okay. Now that I've created the first instance, I want all 16 to look exactly like this one right here. So I'm going to go up here under the design menu, under the rooms submenu right here, and I'm going to say copy room formats. As soon as I do that, I get the large crosshair. But if you look at your status bar, it says choose source room. I'm going to click on this one right here. And as soon as I clicked on it, the message now here immediately says choose destination room. I need to only choose any of the others. I'll click on this one, for example, right here. It's going to tell me there's all 16. I can either let it redo room 1, but I know this is room 1. I picked room 1. So I can tell it I don't want to do room 1. And I'm going to click OK right here. And it immediately made all 16 copies exactly laid out, placed, routed, whatever you want to call it, exactly the same sort of. Now I'm still in the action mode, so either right click or escape to get out of that mode. The last thing I'm going to do over here is I'm going to explain one other little feature of Altium here. And for those coming back, and yes, Kevin, looks like a question out there. Sorry, I missed your hand was up.
Is this, are you saying this feature is only for hierarchical design, or can you do this with a room that you've used when you've used like flat design?
So in version 23, in the beta version, I don't know if they just released it in the new 23.10.1 that they just released. They are starting to implement a copy room formats for flat designs. I'm not exactly sure how that works. I haven't played with it yet, but this copy room formats was originally intended for these hierarchy designs because you need the way the hierarchy works is every component gets the same base designator, like R1 or DS1 or whatever it is, and then an underscore and an index. So DS11, DS or R11, R12, R13, and so on. And so it has this in the background, it has this thing called a channel offset, where it basically says, yes, all 16 rooms right here are the same structure. So it knows, it has a way to know, okay, this particular resistor instance in this room is the same resistor instance in all the rooms, so it knows how to do that. So in theory, it's all for the hierarchy designs. They claim they're implementing it for flat designs. I haven't played with that feature yet. It's brand new, literally 23.10. I saw that it came out in the beta, and I saw a few other users on the beta forum that said, yeah, it's kind of working. Kind of cool. I just personally have not played with it yet to see how it works for flat designs, or what it takes to set up for the flat design. All right. Okay, so last thing I'm gonna say, again, for people coming back from PCB 1, you have seen this before. For people new to Altium and new to this course, the green box, blue box select. So when I start making a selection box, if I click my button right here and start drawing a box to the right from wherever I started from, you'll see the box turns blue. From the same point, however, if I move to the left, over here, you'll see that my box will turn green, maybe. And we're going to go like about 5 minutes past this. I'm going to show you one last feature here and then turn you loose to keep working on the other circuits. Yeah, there it was. So again, from over here. So if I have a box right here, if I go to the right, it's blue. If I go to the left, it's green. A blue box means the feature I wish to select must be fully enclosed within the box. A green box means the feature only needs to be touching the box. So as an example over here, let's say I want to select these vias here, but not the little traces that I routed here. If I do a blue box, I can go around the two vias like that, but I have not fully enclosed the two traces, so only two vias get selected. If I go the other way, however, with a green box, not only am I going to select the traces, I'm also going to select both components. And I've selected everything. Now, I show you that because I'm going to throughout the duration of this course, I'm going to constantly be saying blue box select or green box select. So I want you to know what I'm talking about there. The other thing is these rooms right here are only selectable with a blue box. So if I want to select the room as a whole, I must do a blue box that selects the room. Even if I fully enclose it with a green box, I only select the components but not the room itself. Okay, so knowing that now, I'm going to go out here and I'm going to do a blue box select around all of my rooms. So the compounds in the rooms right there, I have all 16 rooms selected. I want to make a little 4x4 array. So what I'm going to do is I'm going to go over here and I'm going to go design the same room submenu now, right here. All right, no, I understand, Mattia. We're going to be done here in like a minute or two anyways, but I understand you got to take off. So I'm going to go over here, rooms, and I'm going to say arrange rooms right here. And I'm going to say I want a 4x4. I want 4 columns, 4 rows. So that's going to be my 4x4 array. I'm going to say assort in ascending order by channel name. So it's going to do room 1, then 2, then 3. So it's going to start in the lower left and increment in ascending order. I'm going to select the origin using my mouse. I'm just going to click my mouse where I want the lower left-hand corner to be. And I'm going to say automatic spacing. So use the room bounding box shape as my corners. And I'm going to say place it onto my grid, even though my grid is set at 5 mils or 1 mil or whatever I have it at. And when I click OK, I'm simply going to go over here and I'm going to say, I know I want them roughly in this upper left-hand corner, maybe about there. And when I click, it's going to instantly grab all 16 of those rooms along with all the resistors, the traces I've pre-routed over here. And you'll see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. all the way up. And you'll see it's properly placed them, evenly spaced, evenly distributed, the whole 9 yards using that arranged rooms. Okay, so now that I've shown you how to route, so from last week, we should have all the rules set up. Again, from our edge page right here, I think I pointed this out last week, but right here in week 3, sorry, week 2, I have this PDF here that says main layout locations. This is a suggested recommendation. This is not meant to be explicit, like you must put it exactly here. In fact, I very much don't want you to follow this to the letter. I want you to use this as a starting guide. I want to see how you as board designers think through the various different challenges, the types of parts, the type of structures, and so on, what you would put where. The main thing is we want input connectors on the left, output connectors on the right, motor drives on the lower right, buttons bottom middle, toggle switches bottom middle, push buttons themselves very bottom edge, digital in the middle right here where we have the processor or the FPGA, memory, and so on. We roughly want the LEDs upper left corner, the LCD top center. We want to have the power supplies kind of along the edge over here. And we want to have our pressure and thermistor circuits over here. Hall effects somewhere. Hall effects are actually going to be digital, so we're going to move those up here in the digital section. So this is just a rough idea. It does not have to be placed square like this. You could choose to put your 2 pressure circuits left to right instead of top to bottom, and then your 4 thermistors 1, 2, 3, 4 in a row like this, however you want to do that. Again, I want to see what you come up with for rationale for how you do it. But following this rough idea, main layouts here, and now we saw how to go through the routing. So your assignment is to start working on the routing. I would recommend you start working on the repeated rooms before you start working on things like the power or the FPGA and so on. The FPGA we'll get to later. But again, you can start working on the various different repeated rooms, and then you can drag the rooms and move them around however you want. So you can either use the arrange rooms the way I did, or as you saw what I did with the LED, after you route a room and resize the room itself, you can come over here, grab a room, and you can actually start moving the room around and placing one room at a time in the design. All right. Any questions on what I did here with the board? Okay, great. If there are no questions, I'm sorry we went over like 5-6 minutes over here today. I will see everybody next week. We will get back on track, and I will copy those material slides, or I might just open up the same slide deck, finish off the information on the conformal codes, because we're also going to talk about application of conformal coding next week. So I'll just integrate those in with the conformal code application, a little bit about the conformal code material in next week. All right. With that, I will wish everybody a happy weekend and happy work week, and go remainder of your work week. I will also say for those that are still having either Altium or DRM or A365, as we talked about, just send that email to education and me, and we'll get that taken care of as we talked about. All right.
Thanks, Chris.
Okay. Thanks, Chris. Have a nice weekend.
Yep, you too, Edson.
I had a question.
Sure.
Is it, so I just realized you were using the beta version. Is it okay to use that? Like, we're using Altium Nexus, which is like 492. I don't know if it's going to be compatible.
So Nexus is not Altium. Nexus is a local version of what they're doing with 365. That's for your data in and out. I'm assuming you're still running an Altium client on your local machine to connect to your Nexus server.
Yeah.
So
yeah,
you are free to use any version of the Altium client.
Okay, and you think that would be compatible with the project? I think it's.
Oh, yeah. I'm on the beta version, but Altium is 100% backward and forward compatible, right?
Okay.
I can do something in 23.10.1, which actually, according to their webpage now, 23.10.1 is under the released version, not the beta version, even though it says beta features enabled on mine.
Oh, okay.
But,
and then,
yeah.
Okay. And then I was able to open up I just want to confirm that the project fall 2018 clean project, that's the one we should start with and set up all the
No, the one that
rules.
says IPC course 2 start point.
Oh,
The clean one,
okay.
you can grab that one for yourself as well. That is my template that I give out to everybody. That's a template project that has, here's my ready-made fabrication drawing, assembly drawing, start points. Here's my, pre-made that has a bunch of .doc and DOT, like schematic files if you want to make your own company templates, update that's got all the editable title blocks and stuff like that in there. And so on. So that is a clean template that I've gotten much praise over, and we'll talk about that when we get to documentation week. And it's also a template I use to make the project, but the actual one for this course is IPC course 2 start point.
Got it. And then I'll just rewatch the beginning lectures. I think you said to set up I want to say I caught the last end of where you were editing the rules. So
Yes.
I believe it's edit the rules and then go into the layout, correct?
Yeah, because if you start routing without the rules set up, all of your trace widths and via sizes and et cetera, are going to be wrong. And then you got to go back and change it all. So yeah.
Yeah. Okay.
Order of
great.
operations: rules first. Rules lead to routing widths and clearances, et cetera. So.
All right.
Yes.
Thank you.
Yep. Not a problem. And then Faisal had a question regarding the weekly assignments. I've said it a couple of times, and again, we've just recently at IPC started using the workspace. But yes, if you are on our IPC workspace, you do not need to submit the zip file. That was before we were able to use the Altium workspace. So I had everybody submit a zip file so I could look at them that way. But yes, as long as you are connected to our IPC education workspace, you only need to save your project into the workspace and do not need to submit the zip file. Great question, Faisal. All right. Any other last questions? I see Jesse and John hung out there as well. I wasn't sure if you guys were just listening for the last questions or if you two had a couple of questions yourself.
Nope, I was just listening to the questions.
Cool. All right.
Yeah, just listening. Thanks.
Yep, no problem. All right, great. Have a great work week, everybody. See everybody next week.
And you, cheers.
Yep. Cheers. Bye.